Okay, so here we see samples A, B, and C. And sample A is has a carbon mass of 14.82 grams and a hydrogen mass of 2.78 grams. So this is all the same element, or compound, I mean. It's all the same compound, but different amounts of that same compound, okay? And sample B is 22.33 grams of carbon, 4.19 grams of hydrogen. Sample C, 19.40 grams of carbon and 3.64 grams of hydrogen. So if we take the ratio of the grams of carbon to the grams of hydrogen for each of them, this is what we get, 5.33 grams of carbon per 1 gram of hydrogen for each one. So the ratio is the same, okay? And that's what we would expect for any compound today, but this is a big idea to them back then. Like, oh wow, that's cool. Like, they really are in the same proportions, okay? So law of definite proportions here. So this is kind of the experimental ways that they showed that. Okay, so after we get Dalton's postulates, we have another scientist come along, J.J. Thomson, and he wants to understand what are atoms made of? What are they composed of? I guess he wants to understand those subatomic particles of atoms. And so he builds this cathode ray tube that has a positive and negative plate, an anode, a cathode right here. And he connects a high voltage to that, okay? And he shoots through this, due to that high voltage, he can shoot a ray of subatomic particles. He doesn't know what those particles are. He just knows that they are part of the atom. So he's extracting something off of that atom, and he's shooting it through this tube, okay? And then he has these plates over here that are positive and negative plates as well, okay? And he can turn those on or off, and he's trying to study the characteristics of these subatomic particles and trying to identify what they are. So he's shooting this particle through the tube, and he turns on the positive plate. So that's this top one right here, okay? And as he turns it on, that ray goes like this. It changes its trajectory, okay? So it bends towards the positive plate. He's like, okay, that's cool. So let's try the negative plate. So he turns off the positive plate, turns on the negative plate. The exact same thing happens. It goes away from the negative plate. It bends away from the negative plate. So what do you think he concludes about this particle? It's negatively charged. It has a negative charge. It moves away from a negative plate, and it moves towards a positive plate. So it's attracted to the positive plate. It's repelled by the negative plate. This must be charged. It must have a negative charge on it. This particle, let's call it an electron. So they call it an electron. And now they have discovered that atoms are composed of negatively charged particles that they call electrons. Okay? They have no idea where these electrons are or how they're organized. In fact, they just think they're kind of just a big mixture of bunches of electrons just floating around there, okay, making up an atom. That's kind of how they're picturing it at this time. All right, well, Milken wanted to understand what is the charge of an electron. What is the kind of the voltage, the charge? Here he's measuring it in coulombs. He wants to know what is the charge of this electron. Okay, so he ionizes these particles of oil, okay, with these electrical charges, and he puts them into his little apparatus here that drops them, these oil particles, And each oil particle has a different charge associated with it depending on how ionized it became. Okay? So you can see oil drop A has a charge of 4.8 times 10 to the 19th. Negative 19, excuse me. B has a charge of 3.2 times 10 to the negative 19 coulombs. C, 6.4 times 10 negative 19. D, 1.6 times 10 negative 19. And E, 4.8 times 10 negative 19. Okay? So they all have different charges, but what he discovered was that this data showed that each droplet is a multiple of this one. So he concluded that the charge of a single electron is this, because that's the lowest number you can get to, and everything else is a multiple of it. I can divide everything by that number and get a whole number. Okay? And so he's discovering the charge of a single electron. This is how much a single electron, the charge of it, he's discovering that charge. Okay? So that's what he discovered, that fundamental charge.
So that's like current, that's not like related to like amps or the columns?
Absolutely. Yeah. What electricity? What is that? That's electrons moving across a wire. That's all it is. I mean, the light that we see here, the metal wire. How do you conduct electricity? You displace electrons. You push electrons from one end of the wire, and that one displaces the one right in front of it, which displaces the next one. Because metals have this ability to allow electrons to flow across them. And so that's why they conduct electricity. Because of the metal bonds that they form have this unique ability to have these sea of electrons, they call it, the sea of electrons that just passes those electrons by. So you just have a source of electrons, and you're pushing those electrons, replacing the ones before it, and then you have a place where those electrons can sink to, and that's where they'll go. And you will conduct electricity by doing that. So yeah, absolutely, it's related. Okay, so they're trying to understand this atom, right? So they discovered electrons. They even discovered protons in a similar way, and so they're identifying these different parts. They found a neutron, so they know that there's a positive, a negative charge, and a neutral charged particle on these atoms. Okay, so they're identifying this stuff, but they don't know how it's organized or what it's doing. So you get these different ideas. So here Thomson suggests the atoms resemble kind of this idea. The positive and negative charges are just kind of distributed evenly throughout the entire thing. They call it the plum pudding model of the atom. Okay, you can see the raisins and everything, and the positive charges would be the kind of the cake part or the pudding part, I guess. I've never had plum pudding, so sorry. And then we have another scientist proposing that atoms resemble kind of Saturn, where you have the positive charges. This is a little better, right? You have the positive charges right here in the center with a ring of electrons going around it, like that. Okay, so they're starting to try to identify these different ideas of how an atom is composed, where are the particles. Okay, and then Rutherford does a famous experiment where he takes a positively charged particle of an atom and he shoots it at some gold foil. So you can see the gold foil right here. Okay, and he's shooting it through here. Here's the particle emitter. And those particles were alpha particles. They had no idea what that was. They just called it an alpha particle. An alpha particle is actually the nucleus of a helium atom. So it's a positively charged nucleus that has 2 protons, 2 neutrons. They're shooting that nucleus, at this gold foil. Okay? And when they're doing that, they're expecting all this really large scatter pattern. Like everything's just going to bounce off and these particles are just going to bounce around, and we're going to see all over the place. We're going to see scatter. Okay? But from that scatter, they were hoping to get an image of what an atom looks like, basically. And what happened was actually unexpected to them. They had no idea that this was going to happen. But they shoot that alpha particle, and you can see this beam practically goes right through the gold foil. Practically passes right through, and then every so often they would see a few scatters, a few identified particles hitting at different parts, and even sometimes behind the gold foil. It didn't pass through; it would hit, but most of it passed right through. Okay, so what's happening? Well, if we look here, this is kind of a simulation of that. Okay, so here's those alpha particles. Here's the gold. Okay, right here in the center of the gold are the nuclei of gold, the gold. Okay, that's where the positive charges are contained in an atom. We know that. They didn't know that, right? And here around it are the electrons. You can see this is gold, so that's that sea of electron I was talking about, those free-flowing electrons. Okay? So they're shooting these positively charged alpha particles, nuclei, through this gold, and you can see most of it's going right through. It's just hitting right here. But what happens when you get a nuclei close to the nucleus of one of the gold atoms? It deflects it, right? It deflects it, or if it hits it right on, it kind of pushes it back. Okay, so you get some going right back, some getting deflected off to the side here, because positive and positive charges are going to repel each other. And so now they're trying to understand this, and from this data, they come up with this idea that that's just another image of it, right? They're passing right through. Unless they hit the nucleus, they'll go back, or they can get deflected by the nucleus and go off to the side. Okay, so that's kind of the idea there. So now they're getting this idea that the atom is composed of a dense region that contains the positive particles, and they call it the nucleus. So most of the atom is just this empty space. That's where the electrons are found, in that empty space. But it's not like filled space. It's just the electrons are in there somewhere. They're not really filling that space densely, right? They're all spread out, and the dense region is right in the middle in that nucleus, and that's where they determine those protons and neutrons to be contained, which actually determines the mass of your atom. The mass, electrons don't really contribute to the mass of an atom. It's just the protons and the neutrons. In fact, if you consider what a neutron actually is, okay, and we'll look at this in a minute, but a neutron is a neutral particle. How did you cause it to become neutral? Well, because you have protons that are positively charged, electrons negatively charged. If you shove those together into a particle themselves, they will neutralize each other, and that's a neutron. So here you have these neutrons and protons in the nucleus of your atom. What if one of those neutrons decays and releases an electron? What are you left with? You're left with a proton, because the electron part of the neutron came off. And now, if I had 15 protons and one of the neutrons in my nucleus decays, now I have 16 protons. From phosphorus, I become sulfur. Okay? So that's nuclear chemistry, but that can happen. But that's what that neutron is, right? It's the positive, the proton, and then negative electron put together. and that forms a neutron. So the mass of an atom consists of the protons and the neutrons. Protons and neutrons weigh almost exactly the same. Neutrons are slightly heavier because that electron part that's associated with them. Okay? But electrons really don't have much mass to contribute to the mass of an atom. You just round out the mass of electrons because they're so light. Okay? So here we have the nucleus. The atom is mostly empty space, which is a strange idea, right? Because I look at everything around me that's made up of atoms and I say, it's not full of holes, Mr. Crandall, it's solid material. Well, that's because the atoms combine by forming bonds within their electrons that hold things together at subatomic, at those atomic levels, which we can't perceive. But everything's full of holes. We just can't see them. They're too small, right? But everything's compacted together to us, but really, it's really just full of holes. If I want to listen to my radio, oh gosh, I'm old-fashioned. Okay, let's see. If I want to receive a phone call on my cell phone, okay, how's that going to happen? I'm inside of a room. Well, because the electromagnetic radiation of that cell signal, I can receive it through the walls, right? I can receive it through the walls. Why? Because there's holes in the wall. That electromagnetic radiation can pass right through the wall, right to my cell phone, and I can receive that call. Okay? If that wasn't true, we couldn't listen to the radios in our car. We couldn't receive cell phone signals, and we would be okay during a nuclear explosion because the radiation would never get to us. That's not true, right? That radiation is going to pass right through those walls, and it's going to affect us because those waves can pass right through the empty space of the atoms. Okay, they're small enough; they can do that. So how big is a nucleus compared to the size of the entire atom? Well, if you take a blueberry and you put it right in the center of this football stadium, that would be considered the size of the nucleus of this atom of the football stadium. So the nucleus is very dense and small compared to the rest of the atom, okay? Which is much larger empty space around it. Okay, so here are the masses of these things. Here we have an electron and a proton have the exact same charge. They're just opposite. One is negatively charged, one is positively charged, but they have the exact same magnitude of charge. That's why if I have 15 protons on phosphorus, I will have 15 electrons to neutralize it. They will associate with it because their charges are exactly the same. Okay? So we have those charges. The mass of an electron, you can see, is 0.000091 times 10 negative 24, which is much, much, much more lighter than 1.67262 times 10 negative 24 grams of a proton. Okay? And the difference here between a proton and a neutron, you can see, is almost just the difference between the addition of these. And that's how you'll get a slightly heavier neutron here than a proton. Okay, now we say that the atomic mass of a proton is 1, basically. And the atomic mass of a neutron is 1. And the atomic mass of an electron we don't even consider when we're talking about atomic masses, really, because it's too light. Okay? So look at hydrogen. It has 1 proton. It's number 1. That number right there, the atomic number of these elements, that represents the number of protons. boron has 5 protons. Carbon has 6. Okay? So if carbon has 6 and its mass is 12, how many neutrons does it have? 6. That's right. If carbon has 6 protons and its mass is 12, it has 6 neutrons as well. Okay? And that's what determines the mass of an element. Okay? Is the number of protons and the number of neutrons in the nucleus of that atom. The electron mass will simply round off anyways. It's not going to really affect the mass of the element. Okay, so here we're seeing the atomic symbol of mercury. So that's how we represent the elements here on the periodic table, by their atomic symbol. Okay, silicon, Si, phosphorus, P, sulfur, S, arsenic, As, bromine, Br. Okay, so that's their atomic symbol. So here is mercury, right? And mercury is actually one of the only metals that is a liquid at room temperature. Well, it is the only metal that I can think of that's a liquid at room temperature. And this right here, this sample of mercury, is pure mercury atoms all together in one sample. It's not just a single atom of mercury there, it's a sample of mercury. And it probably has a mass, let's say it has a mass of 200.59 grams. Well, it has 80 protons, has a mass of 200.59 grams. The rest of it's neutrons, okay? But the thing that we should be recognizing, the disconnect here, is that if I have, on my periodic table, I have the number of protons and the number of neutrons. If I say I have 5 protons in the nucleus of a boron, and the mass is 10.81, how many neutrons do I have? Wait, that doesn't make much sense, right? Because is it 10 or is it 11? Do I have 5 or do I have 6? The answer to that question is you have both. Because boron 10.81 does not represent the mass of a single boron atom. It's the average mass of an entire sample of boron. So do we have different boron atoms that weigh different masses? Yes, we do. Okay? And those are called isotopes. Okay, so here, this is how we identify the masses and such of an atom. Okay? We write the mass number here, we write the atomic number here, and we write the charge of an atom here. It's very convenient to do that because just like we saw earlier, if I know the mass and I know the protons, I can simply subtract those to determine the number of neutrons. Okay? How many neutrons are in magnesium 24? If magnesium has a mass of 24, how many neutrons does it have? 12? 12 neutrons, 12 protons. This one happens to have a charge of 2 plus. How many electrons does it have then? That's a trickier question. It has 10 because it lost 2 electrons. It had 12, it lost 2, now it has a positive 2 charge. Okay? So here is an alpha particle because all it is the mass of a helium atom with 2 protons. It lost both of its electrons and it has a mass of 2 plus. That's an alpha particle. Okay? This is magnesium 2 plus. It has 10 electrons. So we can identify a lot about the atom if we're given this information here. Okay? And you really don't have to be given this one, because you will always have this where? Where are you going to have that information? Where are you going to find it? Right here. Helium has 2 protons, neon 10, fluorine 9. That's its atomic number. I will always have that. Okay? Could I ever have a helium with 3 protons?
That would be lithium.
Yeah. If I change the number of protons, I change the element. I change your identity if I change the protons. If I change the number of electrons, that's okay. I can do that. And I will have a charge like this. If I change the number of neutrons, that's okay. I can do that. You're still going to be that atom. It's just you'll have a different number of neutrons, which will change your mass. You will either be heavier or lighter, but you will still be boron, or you will still be helium, or you will still be magnesium. Okay? Now, the stability of your nucleus changes as well if I change the number of neutrons. Okay, so here's a way that we can actually see some data. If I take a sample of zirconium and I pass it through a mass spectrometer, okay, this is what I find. I find that there is a zirconium that weighs 90, one that weighs 91, one that weighs 92, 94, and some that weighs 96. And you'll see they're all at different proportions. There's much more zirconium 90 than any of these others, right? Okay, so that allows us to see that you can have the same element with different masses. What is the difference in their mass? What's causing the difference in their mass? Why is this one 90 and this one 91? The number of neutrons. Zirconium has how many protons? 40. So if I'm zirconium 90, how many neutrons do I have? 50 neutrons. If I am zirconium 91, how many neutrons do I have? 51. I have one more, right? I went from 90 to 91. 52, 50, where was I? 52, 54, 56. Right? It's the number of neutrons that's changing. And as it changes, it will increase my mass, make my sample, that zirconium atom, heavier and heavier and heavier. Okay? Or if you get rid of neutrons, it'll make it lighter. But as long as the number of protons remains constant, I will still be zirconium. If I change those protons, I will change the element. Okay? All right. These are called isotopes. Isotopes are an atom. If you have an isotope, you have an atom that has a sample with different masses of that atom within it. So zirconium here has 1, 2, 3, 4, 5 isotopes within that sample of zirconium. Now, are all of those isotopes stable isotopes? No. Some of them are radioactive isotopes, and they can decay. So every element has isotopes. Carbon has isotopes. We have carbon 12, carbon 13, carbon 14. How many neutrons are in a carbon 12 atom? 6. And carbon 13, carbon 14, 8, right? That's the difference. It's the number of neutrons. Other than that, they're the same. They have the same reactivities. Everything else about them will be the same. It's just that one is heavier than the other, and one is more stable. The most stable isotope of carbon is carbon-12. It is the carbon in the greatest abundance. Most carbon that we find has carbon in the form of carbon-12. But every sample of carbon will have some carbon-13 and carbon-14 in it. So if I go and I burn some wood, and you're left with the ash, carbon, that carbon sample will have some carbon-12, carbon-13, and carbon-14 within it. You are organic human beings. You're organic organisms. Guess what? You're made up of a lot of carbon. And your carbon inside of you is made up of carbon-12, carbon-13, and carbon-14. You have all those isotopes in your carbon within you. Every organic molecule does. Okay? So, does that mean that we should be worried because some of these are radioactive? Carbon-13 is radioactive. So are we radiating each other? And sure, I mean, it's radioactive, but we deal with radiation every day. The sun is more radioactive than, it's going to be more harmful than the carbon-13 in us, because the carbon-13 sample is so small that it's not going to bother us, okay? So the carbon-13 within that carbon sample is, if I go weigh out some carbon in the laboratory, I'm not going to have to put on all my radiation equipment, because the carbon-13 in that sample is not, there's not enough of it to be bothersome. Now, if I enrich the carbon-13, I isolate the carbon-13 from all the other carbons. Now I'm worried because I have an enriched sample of radioactive material. Okay? And that can be dangerous to me. So I want to be more careful. Okay? But just having a regular sample of carbon, it's okay. It's not, or anything. We go weigh out chemicals in the laboratory all the time. And those chemicals contain the isotopes of itself. Okay? Phosphorus. Phosphorus has phosphorus 30, 31, 32. Phosphorus 32 is radioactive. They use it in research, like when they want to look at DNA. They can put a phosphorus on that DNA that's radioactive, and then they can see the DNA in their scans and things like that. Okay, so because it will illuminate their film. It's like taking a picture of it, right? And that radioactivity will illuminate a spot on their film, and they can identify the DNA, its masses, and different things about that, etc. So we can use radioactivity to help us in certain ways, but every sample has radioactive isotopes. We're not worried about them because those radioactive isotopes are in low enough percentages of that sample that they're not going to bother us. Okay? Everything around us is like that. So if I go to the laboratory and I want to weigh out a sample of aluminum, I need to do it to 26.98 grams to know exactly how many atoms of aluminum that I have. Because if I weigh it to 27, that's wrong. That would be for one isotope. Or to 26, that would be for a different isotope. But the sample is of all those isotopes put together, so I have to weigh it out to 26.98 grams to know exactly how many atoms of that I have. Because that mass right there on the periodic table is related to the exact number of atoms that you would have in a sample measuring that mass. So I weigh carbon to 12.011 grams, and I know exactly how many carbon atoms I have. If I weigh it to 12 or 13, I don't. Okay? Well, I could figure that out, but it would be in relation to this, 12.011. All right? If I have 12.011 grams of carbon, I have exactly I have exactly 6.022 times 10 to the 23rd atoms of carbon. Or if I measure out 78.96 grams of selenium, I have exactly 6.022 times 10 to the 23rd atoms of selenium. Or 24.305 grams of magnesium, I have exactly 6.022 times 10 to the 23rd atoms of magnesium. That's how the periodic table helps us, because it's giving us the amounts per the number of atoms. It tells us exactly how much we have if I measure out that sample. And that is only because we have determined the average masses of a sample of these things. That includes all the isotopes. And not just one, but all of them. And it creates a weighted average of those. Okay? So let's see how that's... we'll see. Okay. Here are some isotopes of hydrogen. Hydrogen 1, 2, 3. You can see the difference in the atomic number is the same. The number of protons is the same. It's the number of neutrons that changes. We have deuterium, tritium. Okay, those are both radioactive isotopes of hydrogen. So if you instead of reacting H2 plus O2 to form H2O, if you isolate a sample of deuterium, D2 plus O2, you'll form D2O, which they call heavy water. They call it heavy water, which is radioactive water. Okay, so that's deuterium. Here we have helium isotopes, lithium, okay, boron, and that's how we get these masses over here. Okay, the masses that we see on the periodic table. Okay, let's see. I think we can. We'll do that some other time. Okay, so how do they do this? They do it the same way you would calculate your grade, like in this class. Even though Canvas does it for you, it calculates your grade for you. If in the old days when I went to school, they didn't have Canvas or a grade book that you could just look at and put a theoretical grade in there and all this nice fancy stuff you guys do today. Okay, but I would have to sit there and I'd have to actually calculate my grade. Okay, I made this. What do I need to make on my finals so that I can get whatever grade? Okay, this is how you would do it. It's a weighted average. So you determine the mass of the isotopes and the percent. And I would recommend making a chart like this. This is how I would set it up when you're calculating these. Okay? So the element boron is composed of two isotopes. About 19.9% of all boron atoms are boron 10 with a mass of 10.0129 atomic mass units. And the remaining 80.1% are boron 11 with a mass of 11.0093 atomic mass units. What is the average atomic mass of boron? So we take the mass of the isotopes. Okay, so they're giving us the exact masses. You could even probably just take 10 and 11, and that would be good enough because it's just going to round out anyways. Okay, but here they gave us the exact masses, so we're going to use those exact masses. The mass of the isotope, 10.0129 and 11.0093. What is its percent abundance? So the percent abundance of boron 10 is 80.1%. So 80.1. And the percent abundance, whoops, that was wrong. 19.9%. Okay? So the percent abundance of boron 10 is 19.9. The percent abundance of boron 11 is 80.1. Now all I have to do is I have to multiply each isotope by its percent. How do you multiply something by its percent? Do I say 10 times 19.9? What's that? Yeah, I have to change it from its percent back into a decimal. How did I get to a percent? I multiplied by what? By 100. You multiply by 100 to get to a percentage. So if I want to change it back, I have to divide by 100 and move the decimal place 2 places. 1, 2. So this is going to be 0.199, and this other one is going to be 0.801. Okay? So now I'm going to multiply 10.0129 times 0.199. And 11.093 times 0.801. What do I get? Do that for me. What do I get?
1.992567.
Okay. What do I get for the other one?
8.8184493.
8.814?
8.8184493.
Okay. Now, how do I finish this?
We're going to take off the numbers, right?
We will, but I want to keep everything as much as I can until we get to the last answer. Then we can round. Okay? How do I want to finish this? I'm going to add these two numbers together, and they're going to give me the average atomic mass. So what is the average atomic mass here?
7.81 10 16.
10.81?
Yes.
Okay. So here I have a lot of significant figures, and here I have a lot. But in the percentages, I only have 3 significant figures. So really, let's see. I would only keep to 2 decimal places because even though I want to keep these in the calculation, okay, this times that would be 3 decimal places. This times that would be 3. And so I would just carry it to 2 decimal places in the math here to 10.81. Okay, 10.81 would be the average atomic mass. I can check it here. Did I do it right? We got it exactly the same. Okay, you don't usually get it exactly the same, but you usually get it close, or you need to get it close to, because it's telling you the answer right here. This is the answer. These are the answers of this. So if you're doing this and you want to check to make sure you're doing it right, make sure you're getting these answers. Okay? They don't have to be exactly the same like we got, okay? But they should be relatively similar. Okay? They should be relatively similar. Okay, let's try this one. Go ahead. You guys try to set it up first, and then we'll set it up together. Okay, so let's make sure you're setting it up right. So we have neon 20, 21, and 22. Okay, so we have 20, 21, and 22. Okay, we're going to first look at their mass, and then we're going to multiply it by their percent, and then we'll get those and add them together. Okay, so the mass of neon 20 is 19.9924, 19.9924. 21, 20.9940, and 22, 21.99. Okay, and neon 20 has a percent abundance of 91.84, so 0.9184. 21 is 0.47, 0.0047. And 22, 7.69. Okay, so hopefully this is how you were setting it up. Okay, And you can always, for these ones, to make sure you're doing it right, just divide 0.47 by 100, and it'll tell you what what to put there. Okay. So you don't have to try to guess. Just make sure you're doing that right. Okay. So this times that is what? What are you guys finding?
18.3610.
Okay. This times that is.
0.098679.
Sorry, say it again.
0.098679.
Okay.
0 before point zero.
Point zero.
0.0, excuse me. Like that. Thank you. This last one.
1.691138.
Okay. And then we're going to add those together. And what is our final mass going to come out to be?
20.1508. That's
Okay, is that where you guys are getting to? What is this for? Neon? Okay. 20.179, that's close enough. Okay. 20.1508. Is that what you guys were finding? Everybody else? Do we have a consensus on that? Okay, good. So if I was going to look at significant figures here, let's see. This has 2 significant figures. I'd take it to right there. 2 significant figures. That has a bunch. That has a bunch. So this has 3, 1, 2, 3, same place. So 2 decimal places right there. 1.15. Okay. All right. There it is. 20.15. We did it right. Okay. Okay, so that's how we do average atomic masses. You'll have some of those on your homework. So in chemistry, we like to represent things. Okay, so now we're moving on. Okay, with models. Okay, and a molecular formula is a representation of a molecule that uses the chemical symbol to indicate the type of atom followed by the subscripts. Okay, so here we have the molecular formula. So that's how we represent the molecule. So molecules are different than atoms because molecules are atoms put together in a compound, right? So here, how do we represent those? We represent it by the different elements in the compound, in the molecule, and the number associated in each position. Sometimes, or not even in each position, sometimes just how many you would have in the entire molecule. Okay. Here we're seeing this carbon is associated with 4 hydrogens. Okay. That's its molecular formula. Its structural formula would show the carbon in the middle with the hydrogens around it. We can also represent that by colors. The black is the carbon, the whites are the hydrogens in a ball and stick model. The sticks represent the bonds between those. The balls represent the atoms themselves. Okay? Or a space filling model that would show more of how the 2 atoms wouldn't really be bonded in this fashion with a stick. They would actually be sharing electrons. Their electron clouds would be actually converging. And that's more of that space filling model, okay, that they would show. Yeah. So that's how we represent a lot of. You're going to see these kinds of things throughout. So just be aware that that's what they're representing as we go through these chapters. Okay, so here's another one. Okay, so here this is a sulfur ring. Okay, and this would be kind of how it would be in the ball stick model, and that's the space fill model back there. Okay, so you can see that ring isn't really here. It's going back. You can't. It looks like it's straight, but it's more going back here, and then okay. That's kind of. If I was to put this model together with my molecular kit, I would see it better in that fashion. Okay, with all those sulfurs. So S8. That's kind of how sulfur exists. It doesn't really exist as a single sulfur. So if you find sulfur, it's in that configuration, S8. Just like you have H2, and O2, N2. So these molecules don't exist as single things in nature. They exist together because they're trying to satisfy their unsatisfied octets, which is we'll learn about. Okay. All right. So here they're just saying this represents a single hydrogen atom. This would represent two hydrogen atoms that are not bonded. But if you say H2, that means that hydrogens are bonded together. One hydrogen bonded to another one. So that's the difference in the notation here. Two H2s, I have two hydrogens that are bonded together. So a total of 4 hydrogen atoms in 2 hydrogen molecules. Okay, that's kind of how I would say that. 4 hydrogen atoms in 2 hydrogen molecules, right? So when we're talking about things, that's what we mean. If I talk about the hydrogen molecule, that's H2. I talk about hydrogen atoms, that's hydrogen. That's a single hydrogen like this. Okay? Okay. Empirical formulas are molecular or ionic formulas that are written in their lowest ratio format. Okay? So you can see this titanium 2 oxide molecule here, or the titanium dioxide molecule. Okay? It looks pretty complicated, complex, okay? And we wouldn't represent it as like titanium 50 O100, okay? We wouldn't do that. Even though here we're saying the structure of it looks like kind of like that, right? We wouldn't represent it that way. We would represent it in its empirical formula. So I reduce it to its lowest formula, and it becomes TiO2, titanium O2. Okay? So the ratio in this molecule here is that you have 2 oxygens for every 1 titanium. Now you don't do that all the time with molecular covalent compounds. Okay? But in this case, because we have the metal and the non-metal, and it's forming kind of this lattice structure, we would represent it that way. Okay? But more covalent molecules that form actual structures like this one. This is glucose. And this glucose has a molecular formula of, here's a carbon, here's one, here's one, here's one, here's one, C6, H12, O6. I'm not showing all the hydrogens that would be coming through here. So that's why you're probably wondering, well, what? Okay. Oh, okay. So that would be the formula: C6H12O6. And I would represent it as C6H12O6. I would not represent it as CH2O. Okay? Because this molecule, that's its structure. That's what it is. It's a glucose molecule. And glucose molecules can associate with other glucose molecules, but they can also separate from one another, and as they do, they retain that structure. They're not changed. And so for covalent molecules like this is how I would represent their formula. Not in the empirical formula, but in the molecular formula that it is. Ionic compounds that we'll talk about, ionic compounds, metal compounds, we do represent in the empirical formula because of the structures that they take, these lattice structures, these crystalline structures that they form, we represent them in the empirical formula because it would be ridiculous to represent them otherwise, because it's always a ratio of the nonmetal and the metal, okay, that form those structures. Now, one interesting thing about this, that's a glucose molecule. Its empirical formula is CH2O. It's called a carbohydrate, a carbon water, right? A carbon water, because its empirical formula is CH2O. All carbohydrates have this exact same formula, C6H12O6. Glucose, fructose, those all have C6H12O6 as their molecular formula, and their empirical formula is CH2O. Disaccharides basically have that same thing going on. Okay, so all these carbohydrates, that's where they get their name from. They're carbon water, essentially. All right. What is the empirical formula of benzene? What's the molecular formula of benzene? Start with carbon, CH. So how many carbons?
6.
How many hydrogens?
6.
So what's the empirical formula? CH. That's the empirical formula. Okay? So C6H6 is benzene. Its empirical formula would be CH. What is the empirical formula of vinegar acetic acid? Say it again, what? C2. 4. Okay, 2 oxygens. What's the empirical formula then? Okay, CH2O. This is not a carbohydrate though. Sorry. That's not vinegar. Yes, it is. Okay. All right. So that's empirical formulas. All right. All right. Our periodic table was developed early on by 2 scientists. Okay. Mendeleev is most credited with the early development of the periodic table. Okay. And this is kind of what it looked like, right? Now, this was a pretty good idea of the elements and how they're arranged, okay? But it's almost in a very similar order that we have it today. But it was arranged by mass. Our periodic table is not arranged by mass. Look at this. If I arranged it by mass, these would be out of place. Right? So that's not how I arrange the periodic table any longer. Okay? The periodic table is now arranged according to the number of protons on the elements, with a lot of other things and that we're going to talk about. Okay? There's a lot of other ways that we've put these elements where they go on this periodic table, and it looks like this. Okay? And that is because it's representing a lot of stuff. The energy levels of the electrons, the sub-energy levels of the electrons. It's representing their masses as well, the protons, all that stuff. Okay, and we're going to talk about that. But that's how it's arranged now. This is kind of the early idea by mass, and which was pretty good. Okay. So let's identify a few things on the periodic table here. An alkaline metal. Alkaline metals are the, okay, so let's first identify what metals and nonmetals are. The periodic table is mostly metals. This red line is the divider. These are the nonmetals. Everything else is metal. All of this is metals. So most of the periodic table is made up of metals with a few nonmetals over here. Okay? So when we identify the groups of metals, one of the first groups is this first column right here, lithium, sodium. And by the way, hydrogen is not a metal. It would be considered a nonmetal. So that's the only exception with that line, okay, when we're looking at that line. Hydrogen and helium kind of pair together. And they kind of go back and forth between where they go on the periodic table. We're going to move helium over here sometimes, and we'll leave it over there sometimes. But everything else, besides that first top group, okay, we identify lithium, sodium, potassium, rubidium, cesium, francium. Those are the alkaline metals right here. Oops. The alkaline metals. That's that first group. The alkaline earth metals are right next to it. Okay? They're that second column or group. So if I say an alkaline, and I'll use that verbiage sometimes. I'll talk about alkaline metals or alkaline earth metals, and you need to kind of have an idea, oh, that's what he's talking about. He's talking about the first column of the periodic table, not the second. We can be talking about compounds that form precipitates in solution, and I'll say if you have something associated with an alkaline metal, it won't precipitate. If you associate it with an alkaline earth metal, it does. That simply means potassium will not precipitate, calcium will. Okay? So that's the difference. These are alkaline metals, these are alkaline earth metals. Column 1, column 2. Transition metals are these metals right in here. Those are the transition metals. Okay? Those are the transition metals. The inner transition metals. These are the inner transition metals. This bottom group right here of metals. You see how if we included those in the periodic, like up in the periodic table, where would they go? They would get inserted right here. This periodic table would expand way out and be really long. And so you would have more of something that looked like this. Okay, that's what the periodic table would look like if I inserted those, right? It would expand it out like that. That's how it would do it. Okay, but so since we don't want a periodic table as long as our wall, we pull those out and we put them down there, and we just realize if I'm following the numbering here, I go from barium 56 to 57 down here, 71, back up to 72. That's how I'm following it. Okay. That's how I'll follow my periodic table. So that's why they're called the inner transition metals, because they're now kind of inside there. Okay, metalloids. So you can see these kind of pink elements right there. Okay, those are my metalloids. Metalloids have characteristics of both metals and nonmetals. So if you think about the characteristics of metals, oh gosh, we're out of time, man. Okay, metals lose electrons, they conduct electricity, etc., etc. Metalloids kind of fall between the metals and the nonmetals. We'll finish that up next time.